Hi everyone. So I thought I'd make a quick video with a little bit more about the quadratic formula. Just a quick review and then just a couple of vocabulary words that I think you'll find helpful. So the idea of the quadratic formula is that it allows us to solve any quadratic equation of the form ax squared plus bx plus c. So a, b, and c here are the coefficients of our quadratic equation, and then we, as always, write the polynomial, the quadratic, in order. So the x squared term goes first, the x term second, and the constant last. Now, I love deriving the quadratic formula. You'll know this about me, more and more as the semester progresses, I don't like just giving you formulas and then using them. But for the interest of time, I'm not going to derive it right now. We may derive it later, or I may just post a handout for you to peruse. I won't test you on deriving it, however. So here's the quadratic formula. The solutions to this equation are negative b plus or minus the square root of b squared minus 4ac all over 2a. And I want to put this off to the side here, kind of as a little bit of a vocab moment. So vocabulary. The piece that's underneath the square root here, the b squared minus 4ac, that actually has a name. That's called the discriminant, and we're going to say a few words about it at the end of this video. So the discriminant is that difference. It's the difference between b squared and 4ac. And as it turns out, the discriminant actually packs a lot of information about what we can expect our quadratic to do, how many solutions we can expect it to have, and what kind of solutions we can expect them to be. All right, so let's go ahead and try a couple of examples. So solve using the quadratic formula. I'm not going to do too many of these examples just because I think you get the hang of it pretty quickly. But you do have some in your homework assignment, and obviously please don't hesitate to ask questions about any homework assignments either in the discussion or in our meeting on Friday. All right, so let's say that we have 2x squared minus 7x plus 2 is equal to 0. Okay, so I won't spoil the fun of you trying it, but if you were to try to find a way to factor this, you would very quickly run into problems. In fact, 2x squared minus 7x plus 2 does not factor, and so we couldn't solve this by factoring if we wanted. One thing that I highly recommend, especially if you have historically struggled with a quadratic formula or you're rusty with it, this is one of those things that you'll do the first time or two or maybe three, and then eventually you're gonna be comfortable without it. So I think it's really great to write out A, B, and C, right? So A is the x squared coefficient, B is B is the x coefficient, and C is the constant. And then looking at the pieces of our quadratic formula, I actually think that it's really handy to find the discriminant. That's the most computationally sticky part of this, so taking a second to do it separately is really helpful. So we have b squared, which is negative 7 squared, minus 4 times a times c. Negative 7 squared is 49, and then 4 times 2 is 8 times 2 is 16, so we have 49 minus 16, which is 33. Okay? So now we have essentially all of the bits and pieces of the formula worked out, and we just have to put it together. So when we do that, we have negative b, so the opposite of b, which is positive 7, plus or minus the square root of the discriminant, which we've already taken a second to figure out, and then all over 2a, which since a is 2, 2a is 4. So here are our solutions. So we have 7 plus the square root of 33 over 4, and 7 minus the square root, of 33 over 4. Now, some of you might be looking at this thinking, oh, what a mess. And I agree with you. These numbers are called irrational, right? So the square root of 33 is not a number whose decimal representation terminates. If you were to punch the square root of 33 into a calculator, you'd notice the decimal representation goes on forever. So, in fact, this is actually the neatest way to write them, or the most complete way to write these numbers. But I do want to point something out, that if you want to get a sense, like, okay, what am I looking at here exactly? You can say, well, the square root of 33, I'm not looking at a calculator off screen. Let's think about, what is the square root of 33? Well, 36 is a perfect square. So the square root of 36 would have been 6. And 33 is not that much smaller than 36. So it isn't a terrible guess to say that the square root of 33 is almost 6. Okay? And if you just want a decent but not great approximation, just something for you to kind of feel like, yeah, okay, I'm in the ballpark, it's actually not terrible to say the square root of 33, it's almost 6. Let's just call it 6 for all intents and purposes. So if you wanted to kind of have an idea of what this number is, you could say this is approximately 7 plus 6, which is 13, over 4, and if you wanted to write that as a decimal, that's 3.25. Now, again, this is a bad approximation. In fact, you'll see I'm very, very, very clearly using the squiggly equal sign, and this is not intended for any kind of precision. This is just to give us a sense of, how big is this number, about where is it, and is it positive, is it negative? If you wanted a more precise approximation, you'd use a calculator, but you'll notice that for the most part, we don't. We use the precise version in almost everything we do, and this gives us a way to kind of have a sense of, okay, what am I looking at here? And by that same token, if you wanted a really ballpark approximation of 7 minus the square root of 33 over 4, well, 7 minus the square root of 3 is pretty close to 1. It's not that much bigger than 1. So for a bad approximation, we could say it's about a quarter. So about 0.25. So without a calculator, without doing anything super sophisticated, we see that this equation has two solutions. One is in the neighborhood of 3, and the other one is in the neighborhood of a quarter. So two positive solutions that we kind of know what they are. I find that to be comforting, personally, the ability to kind of have a sense of what the number is without using a calculator. So that's how we use the quadratic formula to solve a quadratic equation. Note, and I'm going to start this example, but I'm not going to finish it. I'll let you finish it on your own. If you have something like x squared minus 4x plus 2 is equal to x minus 7, and you're told to use the quadratic formula to solve this equation, I'm only going to say this much. Set to 0, set equal to 0 before deploying the quadratic formula. And this is key. The quadratic formula presumes that you are working with an equation that's already set to 0. Okay, so in this case, what you would probably do is you would subtract x and add 7 to both sides before you started to use the quadratic formula, but then from there, it would be just like what we did in the previous example. So the last thing that I want to talk to you about in this video is I want to circle back and I want to revisit the discriminant. So what does the discriminant tell us? Well, the discriminant is the number underneath the radical. And in some sense, that's the most important portion of the quadratic formula. So we break down the discriminant by all of the possible options for it. So it could be negative. It could be equal to 0. It could be positive. But in positive, and I'm actually going to get to in a minute, there are two ways this could go. So we're actually going to expand this a little bit. So if the discriminant is less than 0, so let's think about what that would look like. Let's think about, you're approaching a problem for solving a quadratic equation using the quadratic formula, and you go through the process like we did in this example here, where you determine the discriminant, and it comes out negative. Well, where does the discriminant end up? It ends up under the radical. So all of a sudden, you're taking the square root of a negative number, which, that feels weird. We maybe even have no idea how that would work, and we've never seen it before. So I'm not going to say a ton about it, except that if you have a negative number underneath a radical, a square root, what you are looking at is you're looking at a value that's not real. So there are still two solutions. And I'm going to leave it here and not say too much about it. There are two solutions, but they're non-real. Notice I'm not saying there are no solutions. I'm not saying this is a mistake. It's perfectly fine for the discriminant to be negative. But when you have that happen, that's a situation where you have two non-real solutions. Okay? The next option that we listed was the discriminant is equal to 0. Well, let's think about that. So again, you've got your quadratic equation, you figure out what your A, your B, and your C are, you think about the discriminant, and it turns out to be 0. So that means that what you have in your quadratic formula now is negative b plus or minus the square root of 0. But the square root of 0 is 0. So I'm going to write this, and then, in fact, let me actually write this. Do you all agree with me as I'm writing this? So I can't see you. I wish I could see you now, but it doesn't matter whether you add 0 to something or take 0 away. Nothing changes either way. So if your discriminant turns out to be 0, you don't have two different solutions the way that we had in our example that we worked out. You have only one solution. Now, it's what we call a repeated solution. And that's important, but we'll talk more about why it's important later. So now we get to the land of positive discriminants. And maybe some of you are getting there with me and others are still kind of chewing this through. But when we're talking about positive discriminants, we are now in the territory of being able to take the square root no problem. But now we have one of two choices. Either the discriminant is a perfect square, in which case you can just evaluate the square root and the square root symbol doesn't need to stay. Or it's not a perfect square, in which case you've got an irrational square root and the square root has to stay. So I'm actually going to break it up into those two options. The discriminant is positive, but not a perfect square. And then the final, kind of the most, in some sense, this is the most nice. This is the one we like the best. Is that the discriminant is a positive perfect square. If the discriminant is positive but not a perfect square, then the square root of the discriminant is irrational. So this is a lot like what we had in our example that we worked out. And if the example is, if the square root of the discriminant is irrational, then you have two irrational solutions. So again, you have two solutions that you could approximate them. You could do a good approximation, you could do a not so good approximation, but in order to write it precisely, you have to leave the square root in. If the discriminant is a positive perfect square, then the square root of d is a rational number. Which means that you don't have to leave the square root anymore. You can actually evaluate it. So like the discriminant might be 25, and then the square root of the discriminant is just 5, and then you can evaluate from there. So if your discriminant turns out to be a positive perfect square, you have two rational solutions. In fact, when you have a perfect square discriminant, this kind of equation would have solved by factoring. So if you're someone that you're all on board for using factoring, but you don't want to waste your time. You don't want to poke around hoping that the thing factors when in reality it's never going to work. Well, quickly computing the discriminant will tell you whether or not factoring will work. If the discriminant is a perfect square, it will work. Otherwise, it won't, and you just are better off starting with the quadratic formula. So a little bit of review about the quadratic formula. This is the second of probably 4 lessons that I'm going to make on using various techniques to solve different types of equations. Thank you. Bye.